Hello everyone. So welcome to our presentation at WACV 2026. I'm Anubhav Sen. I'm from the Department of Electrical and Computer Engineering at the Georgia Institute of Technology. So today I'll be presenting our research on SSMRadNet, an efficient and ultralight framework for radar segmentation and object detection. The core challenge we address is that high resolution FMCW radar frames with increasing number of chirps, samples, as well as antennas blow up compute, memory, latency in traditional point cloud CNN transformer based radar object detection pipelines, constraining the real time operation and edge deployment on robotic hardware. To solve this problem, we developed SSMRadNet, the first multi scale state space model framework designed explicitly for FMCW radar data. So, by leveraging the spatiotemporality of ADC radar data, and by sequentially processing the raw ADC samples on a sample by sample basis, our architecture completely eliminates the memory and latency requirement associated with buffering ADC cubes. Consequently, our model achieves significantly lower computation and processing latency while still maintaining strong detection performance. Let's look at why existing methods struggle. So, the state of the art detection methods typically require a Fourier transform over entire radar frames, which forces a frame by frame processing paradigm that increases latency and buffering. Furthermore, standard or learnable fast Fourier transforms ignore the sequential dynamics and smear non stationary spectra. When paired with backend convolutional or transformer models, the computational and memory costs grow non-linearly as the number of chirp samples or antenna increases. This usually happens with increased Doppler resolution or range resolution or even angular resolution due to requirements in different scenarios. Now, why state space models? So, first of all, SSMs are largely unexplored for radar data. However, because radar generates ADC streams sequentially in the form of chirps over time, this data is perfectly suited for time domain linear sequence modeling. Unlike transformers that scale quadratically, and SSM's computation scales linearly with sequence length. This allows us to achieve streaming detection without waiting to buffer an entire radar frame. Now, our approach shifts away from the traditional SOTA methods. As you can see in the state-of-the-art methods, how the radar data is collected over chirps, and finally they accumulate to form the ADC cube, which is passed through FFT encoders to form the FFT cube, then finally passed to the convolution decoders, which creates extremely high latency for larger resolution data as the 3D data size increases exponentially with increasing resolution demands in the future. Instead, our SSMRadNet leverages this pure sample-wise processing to handle the streaming sensor data incrementally as it arrives. This is development over the previous recurrent methods such as chirp-net introduced in IMS 2024, which ignores the relation of the sampling over time and thus mixes the range information, leading to reduced accuracy and higher computation. We solve this problem by mainly using a hierarchical SSM based structure which introduces a sample by sample model as well as a chirp by chirp model, thus compressing the radar data to form the bird eye view feature maps which help us in detection and segmentation. Now, a quick background on the hardware we use. We use TI Automotive FMCW radars to benchmark our models. These sensors implement MIMO through time multiplexing via the transmit antennas. This mixing process yields intermediate frequency IQ channel data, which is organized into chirps to form a complete radar cube. Looking at the landscape of the previous research as discussed, the traditional models are computationally extensive because they rely on processing these large volumes of data, and with increased resolution they grow quadratically. So we bypass all this and scale linearly in computation with increased radar resolution, achieving state-of-the-art performance at a fraction of the computational cost. Now, going further deep into our architecture, our method relies on three operational steps. First, we perform per sample embedding, turning every fast time ADC sample across all antennas into a distinct token. Next, we apply the sequence modeling in two dimensions: intra-chirp modeling along the sample dimension and inter-chirp modeling across the antenna, across the chirps. Finally, the spatial decoding projects the sequence outputs to a 2D spatial feature map used for segmentation as well as vehicle detection. Going To view the architecture as a whole, SSMRadNet operates end-to-end directly from raw radar ADC samples in a sequential fashion. The per chirp sample states are aggregated into chirp feature maps, which are produced from a Mamba SSM block. These produced bird eye view occupancy map is then fed directly into the detection and segmentation head, which produces the detection map as well as the segmentation map. These detection and segmentation maps are later used for planning purposes, mapping purposes, as well as predictions. We evaluated our framework on the RADIal as well as the RADIal datasets. The RADIal dataset contains 91 driving sequences utilizing an HD radar setup featuring 12 transmitters and 16 receivers. Qualitatively, the segmentation performs very well on clear highways, though some errors naturally arise with dense traffic, as we can see here, as well as when the difficulty grade increases. The inclusion of these prior chirp states, which we see here, clearly aids in prediction accuracy, and adding explicit motion or elevation priors in the future could further harden these predictions. Furthermore, I would like to discuss an interesting finding which emerged when we were analyzing the feature evolution across the model. As the number of chirps increases within a frame, the state we observe quickly saturates. The spatial cues accumulate rapidly, forming a stable projection within a fraction of the number of chirps. In this case, the knee point has been observed between 32 and 50 number of chirps, as you can see from the diagram. Because these additional chirps contribute diminishing returns in decoding the scene, we intentionally use fewer chirps to cut computation with only a minor trade-off in Doppler resolution. This brings us to the fact that we can do further research on this, how to adaptively select a number of chirps to cut compute when the uncertainty of the scene is low. We also experimented with state retention between the frames. So carrying the SSM state over yields smoother updates and a slightly higher segmentation performance when resetting the state. While resets cause sharp performance dips at the start of new frames, the state retention stabilizes early in steady scenes, though it can momentarily underperform during abrupt scene changes, as you can see from the seventh scene from the diagram above. So this opens door for adaptive interframe interference to save computation. We have done this follow-up work as well, which will be presented in CVPR 2026. Now here we share the dataset and the training parameters. So our training parameter pipeline utilized the Adam optimizer and was evaluated over 200 epochs. Quantitatively, SSMRadNet achieves state-of-the-art segmentation performance on both the RADIal and the RADIal datasets we have used for our evaluation. For object detection, our scores are highly competitive. However, our average recall indicates more false positives, pointing to a need for better dynamic object versus clutter identification, which basically shall look forward to better decoder design for such tasks. So here you can see the performance of our model on both the datasets. We have benchmarks against several convolution, attention, and recurrent based methods, which are the prior state-of-the-art methods. And we find that SSMRadNet performs reasonably well with almost 60x parameter reduction, as well as 100x reduction in computation, as well as around 4x reduction in latency. We furthermore performed some ablation studies where we replaced the Mamba SSM block with S4, resulting in a 3% detection accuracy drop. This highlights that time-varying selective SSMs are much better suited for modeling the complexities of ADC data compared to models like S4 and S5. To prove edge viability, we deployed our model on an Interbotix Locobot equipped with a radar sensor and an Intel NUC edge processor. We observed that SSMRadNet achieved a 1.7x inference speedup on the robot platform, as well as a 3.8x speedup on a mobile GPU compared to over the existing state-of-the-art models, which shows our model is highly energy efficient and it will scale better with increasing radar resolution. In closing, we would like to I'll conclude by saying that we introduce SSMRadNet, which provides a 33x reduction in model complexity, 88x less computation, and a 3.5x reduction in runtime compared to baselines like TF50RADNet and F50RADNet. It is highly energy efficient and perfectly suited for lightweight edge deployment. Moving forward, we plan to refine the dynamic object detection performance, extract the velocity by retrieving the Doppler information from learned representations, and also look forward to adaptive chirp inference and test the model's robustness against noise and clutter. Thank you for your time and attention. I'm happy to take any questions all of you might have. Looking forward to a healthy discussion and improving upon our work. Thank you.